All right, so let's get started. I was actually going to put a slide in here. I didn't. Next Tuesday, we have a guest speaker who will be guest speaking via Zoom. So, since you're the people who are actually physically present, if you really have a super strong desire to come here and watch Zoom, please speak up now. Otherwise, I will probably just do this as strictly a Zoom class. It'll actually make it easier for me to stream it, since then I'll have two computers with way more capabilities. So, do any of you really have a strong burning desire to sit in the room for a Zoom? I didn't think so, but there was one person who wanted me to show up regardless of what the weather was like, so I showed up, damn it. And then the weather turned out to be fine. The other reason I think that this is an advantage is that, of course, since we are going through a time change, this class will be starting at what will feel like 7 a.m. instead of 8 a.m. Yeah, it's Sunday. Yeah, I got a slide on that. So, project 4 is due on Monday. And of course, that's a great thing to do before a Tuesday thing. It is still, you still have the late date. So if you're below 75%, you can go back and work on that. I would strongly suggest that you not sacrifice project 5 for project 4. So if you don't make, let's say you're sitting at 60% for project 4, move to project 5. It is decoupled from project 4. Focus on project 5, and then if you get project 5 done early, then you can go back and work on project 4. But don't make the reverse sacrifice. Don't take the thing that's worth fewer points and work on it at the expense of the thing that takes more. And project 5 has different parts that you're going to find are easier or more difficult. I mean, it's actually pretty easy to just simply put a KV store on top of Paxos. What becomes more interesting is when you start trying to do reconfiguration. And we're going to be talking about that today, actually, just a little bit. So April 13th is the hard deadline for everything because that's the last day of classes. That's the last day that I can have things due. So, and then a week following, on the 20th at 8:30 in the morning, we will be doing a final exam, which of course will put everyone into a panic. There won't be a lot of questions on the final exam. I haven't decided exactly what there will be on it yet, but there won't be a lot of questions. My goal is not to make you sit there for 2.5 hours and work on it. How's that? I think that's just cruel and unusual punishment. Let's see, the other thing that I mentioned is, yes, we are switching from Pacific Standard Time to Pacific Daylight Time. One of my personal pet peeves, people always say PST when they really mean PDT. And I find it confusing because I work with people in all sorts of different time zones, and I don't want to keep track of whether you do daylight time or not, because there are provinces in Canada that do not use daylight time, and there are states in the United States that do not use daylight time. And we could just adopt one time, it would be fine. It should be like China. Right? Spans 4 time zones, but only has 1 time zone. I don't know. Maybe someday we'll stop doing this again. Yeah, but they won't do anything until the U.S. does something, because it doesn't make a whole lot of sense to not keep things synchronized. This is like a distributed consensus protocol where we don't have replicated state machines. We didn't even talk about that problem, but this is the real world we live in. I don't think there's anything new here, so I'm not going to really talk about it. So a couple of links to things that I'll be talking about today. So this is a more pragmatic kind of lecture talking about why are we doing all of this hideous work with Paxos? It turns out that these distributed consensus protocols are very heavily used, and this is going to be an example, a couple of examples that come out of Facebook, which I think is now called Meta. It's the same protocol. So yes, underneath it, it's always Paxos, but different people implement how they're using it differently. And as people who we were just talking about before the class, if you've been working on Project 4, one of the challenges there is that it is really a log replication protocol that is using Paxos to come up with a consensus on what the log looks like. It is not the only log protocol. So the reason that people seem to like Raft is because it's better documented or easier to visualize. And yet it still seems to be really hard for people because PMMC and Raft are very similar. They're not exactly the same, but they're very similar. And as I was saying before, the other thing that I've found, and we're going to talk about more here, is that often we don't actually want strong consistency. Strong consistency is part of what makes reasoning about this very challenging. We want a strongly consistent database, but it turns out that in many cases, we don't want to pay the price of a strongly consistent database because, gosh, it's really complicated to implement, it's hard to get right, and it can take a long time to reach consensus. We've been talking about key value stores, and why we choose key value stores is because they turn out to be wildly useful. And I had never really thought of, I've been building file systems for decades, and I've never really thought of like a file system as being nothing more than a key value store, but that's exactly what it is. It just has a very limited key space typically. So we give each thing we create an identifier, an inode number, and then we fetch things based on that identifier. That's just a key lookup, isn't it? So when we move to the key value store model, it's really kind of the same thing. And I hadn't thought about this, but in fact, years and years ago when I was working on AFS, which was a distributed file system, one of the things we did is we actually relied on the ability to open a file based on its identifier. And NFS does exactly the same thing, because when we send an NFS handle across the network, the traditional implementation is to embed that identifier in the handle so that when we get a request 2 days later, we just simply open up that file by handle. We don't have to know what the path is. It's much more succinct. Okay, so yeah, there's a naming layer on top of it, but there's a naming layer across the internet too. And yet what we do is we turn it into an IP address. Gosh, it's just a key value store. Wow. So this key value store model is actually a very common one, and it shows up in the internet because when we start using HTTP, we use puts and gets. And we can add other things in there too. Pretty sure there's a delete, but guess what? Now what we're talking about is a key value store protocol. It looks just like a key value store. You may not think of it that way, but when you do a get on a URL, what you're actually doing is a get of something based on a key. When we look at Amazon's S3, that's exactly what it does. Its key is an arbitrary string that conveniently enough you can just happen to put path separators into, which will have some meaning to you, but they don't mean anything to S3. They actually have no inherent understanding of paths in S3. Anybody in here heard of Facebook? Yeah, it's what old people use, but I mean, you won't even remember MySpace. What people who thought Facebook was what was new, that's what people use it for. This is actually a failure that I really liked. There's several of them in this book, and this is a very good book if you actually want to look at how distributed systems are really used in the real world and how real problems actually occur. And this book has a number of case studies. This is one that about an airline. And the reason that we see airlines occur here over and over again is because they actually have all of the real problems that make distributed systems interesting. They are geographically dispersed. They are complex. They have ever-shifting requirements and demands. They are trying to solve really hard problems. Do you know how gates at an airport are actually assigned? Turns out there's one company in the world that builds the software to do this, and it uses an AI algorithm, a machine learning algorithm to do it. It's an NP-complete problem. I mean, it's a really hard problem, and it constantly shifts and changes because, of course, a little bit of delay in an airplane means suddenly everything else has to shift around to accommodate that. This isn't so complicated. This is just a database, a replicated database. This is project 3. Yeah, project 3, right? We got a primary, we got a backup. It's this simple kind of replication, not this complicated kind of replication that you're looking at in project 4. But it's using real things. So we have lots of redundancy at lots of different levels. We have a Java enterprise environment where we're running Java applications because, of course, Java is a universal language. We have replicated data storage. Are you familiar with redundant arrays of inexpensive devices? RAID. RAID is a technique that we actually use. It's kind of like something between project 2 and project 3, where we can use 2 disks and keep 2 copies of everything, or we can use 3 disks and keep 1.5 copies of everything. When we start talking about project 5, when we talk about sharding, we're going to be using exactly these kinds of partially overlapping data elements. If I have n disks, I can keep n minus 1 worth of disks worth of storage and still have redundancy. I can tolerate the failure of a single drive. Gosh, that sounds an awful lot like the whole Paxos thing, doesn't it? In fact, you can actually have multi-drive sets where you can absorb more than one failure. We don't typically do that with drives, disk drives, but we do this with databases. When we get into project 5, our motivation is going to be, how do we take a large database and split it up? And that's not too different than some of what we're going to be talking about today. It's just that it's a slightly different workload. But that's going to get, once we get past the failure. So they have twice daily offsite backups. They have a hot on-site spare that's within 5 minutes of the last changes, so they won't lose more than 5 minutes worth of activity. They use a redundant Oracle database. I don't know anyone who likes Oracle, but they're a very large company, and I'm sure the people who work at Oracle probably are at least appreciative of the paychecks. They had redundant network load balancers. They had a backup facility in a physically separated data center that was, I don't know, 30 or 40 kilometers away, something like that. And this is old enough. This is probably in the early 2000s that they actually did take their database offline to do maintenance on it. This is no longer the norm. These days, we do these kinds of maintenance activities online. But sometimes you still have to take things out of commission. This sounds kind of crazy, but in fact, actually before this time period, Digital Equipment had VMS, which was probably one of the early operating systems that supported clusters. And they actually were able to take individual machines out and upgrade their operating system and put them back into the cluster. So you could do rolling upgrades. So this isn't a brand new idea. It's actually a fairly old idea. So routine maintenance, they switched the primary to the backup. Gosh, this is project 3, like I said. The actual change from the primary to backup was opaque to the clients because it used an IP address that got rerouted. So they had a virtual IP address. Thought it was weird reading that description and going, all IP addresses are virtual, just arbitrarily assigned, but okay. And then they updated the old primary, and then they switched back to the old primary, and then they updated the new, so the old backup. And 90 minutes later, they're done. Hit the slide. Kind of dumb. Okay, so now here we are. It's Friday morning. It's 2:30 in the morning Pacific time, which is interesting because he doesn't actually in the book he doesn't actually say what airline it is, but this does significantly limit the choice in airlines because there aren't that many that are based in Pacific time. 2:30 in the morning Pacific time, the airline kiosks all stop working everywhere. No one can check in. Oh shit. The problem with 2:30 in the morning Pacific time is that it's 5:30 in the morning Eastern time, which means that there are people who are now showing up at the airport expecting to get on their 6 a.m. flights, and they can't check in. Oops. Things are really bad. Of course, what do we suspect happened? It must be the last thing we did, which was, of course, that database upgrade. So, big stressor. The person who's writing this is on the team that is responsible for getting this fixed as quickly as possible. They have an SLA that says we will fix it within an hour. Can you say stress? You think that the Project 4 deadline is stressful. Imagine being told, sorry, we're losing $5 million every 15 minutes, and you have to fix this before we've lost more than $20 million. Okay. So they restarted, reboot, if in doubt, reboot. So we restart the core facilities, doesn't fix it. Somebody comes up with a clever idea of restarting the kiosks, and that fixed it. Well, if the problem was in the core facilities, why did rebooting them not fix it? And if the problem was in the kiosk, why did we think it was in the core facilities? So what was fun is looking at the postmortem. And what was really cool about this, because people have been complaining about, how do I figure out, how do I see these things, whatnot? And the answer is, you log the crap out of everything. You keep as much information as you possibly can. And what I thought was really cool about this one is that in this particular case, it was actually the logs they extracted of the Java threads themselves, the Java applications themselves. There's a signal you can send the Java virtual machine, which will capture the thread state of all the threads in the Java virtual machine. And this guy is actually digging through these to figure out what really caused the problem. There's a resource leak. They're using JDBC. And JDBC experienced an exception because of the database rollover, but the exception was not actually processed properly. So what we ended up with was a connector that really didn't work right, but didn't die. So we have a zombie connection, and we have a thread pool, and all of the threads in the thread pool pile up on this zombie connection, and so no one can query the database. And that's what causes the kiosks to freeze. A single uncaught SQL exception brought down the entire system. I mean, if you actually are building distributed systems, these are the kinds of problems you will end up debugging and moving things down to. I've used misconfigurations. This was a software bug. One unhandled exception. I hate exception handling. I've always hated exception handling. But, and that's because, of course, one of the early bugs I had to debug is a case where I was writing an application that talked to a server, that talked to another server, and they all used exception handling. And so my application would core dump. And so I had to go to the first server and find out that the first server was doing nothing more than propagating back an exception that had been raised by the second server. So I'm literally running the second server under the debugger. I've got 3 different things running under the debugger, watching them going, what the heck? A bug in the second server was caught and sent back. So an actual software bug in the second server was reflected in the application program core dumping. We've talked a lot about consistency. One of the things that I've definitely noticed that people don't quite appreciate, and that's why I asked today about the background in databases. And probably next time I teach this, I'm going to spend a little more time talking about how we actually build consistent databases. So a database by itself is not consistent. In other words, let's suppose that I take my Oracle database and I run it, and then I just turn the machine off, and then I go look at the data in the database. It's actually not in a consistent state. There's a log. The database, once the log has been applied, will be consistent. A common mistake I have seen a number of times is that people are building implementations where they say, oh, any of my servers can read from my key value store. Okay. But they don't realize that maybe the key value store is not up to date. Well, how can that be? We just ran this whole consistency protocol to make sure it is. Yes, but the consistency protocol made sure that the log was consistent. So you have to make sure you don't read around your log, or otherwise it's kind of like reading random state off of the disk. That's not what you want. What's really weird about logs in databases is that you literally can have empty, completely empty databases and have a big log. And so you read the database, you're going to say, there's nothing there. There's no key with that name on it. But in fact, there is one because it's in the log. And so the PMMC paper does actually talk about this. It's hand wave, we'll throw that in. Oh yeah, you have to serialize your reads against your log, but you don't need a slot for them. Well, that's because they don't mutate any state. When you get a read as a server, you need to make sure that anything that's currently in flight has been resolved before you answer that client back. Otherwise, you might have a change that hasn't been recorded in the actual key value store, and you're going to expose out the client. Well, remember the ACID properties isolation. If I show this indeterminate state, I've violated my ACID properties. I'm not giving you consistency, and I'm not giving you an isolated view. Another thing that happens here is that, and I've seen this as well, is people point out, but wait a minute, if I actually have two clients that are each modifying the same key, one client does a put and then does a read, and the other client does an append and does a read, I don't know what they're going to get. And the answer is, you're absolutely right. The consistency model here isn't that it's going to be consistent over time, only that it's going to be consistent at the time that we get your request. There's no guarantee when you read a piece of memory in a program, that piece of memory won't change 1 nanosecond later. What do you do to prevent that from happening? This isn't a rhetorical question. It's actually a legit question for you. How do you prevent that? That's not the usual solution I was thinking of. I'm trying to think of how so I would know that this read was a version number. You could do that. Versioning is one way of detecting that things have changed. Yes. It's not necessarily the classic way that we usually do it. Anybody have anything else? Go ahead. How do you prevent if you want to do a read modify write cycle on a value? You're making it way too complicated. Use a lock. You just use a lock. You synchronize. Now, maybe the locking protocol is running on top of Paxos, but you just use a lock. You say, don't touch this. Read, modify, write, release lock. And now you have a transaction. Now you have an atomic operation. That's it. So if you're sitting at a higher level on top of a key value store and you want to change keys, two different keys that are not otherwise related, you're going to have to build a locking protocol. Not my problem. I'm giving you a key value store. You want some higher level semantics off of that? Have at it. In today's examples, we're actually going to be looking at something much simpler, which is in fact the norm. Literally, this is a case where we have a workload where reads happen 100 times more often than writes. In the internet, anybody know about HTML? Ever actually looked at an HTML page? I mean, you load it up in the browser, you can type Control U in pretty much all the browsers and it'll show you the code behind it. It's sort of fun to look at. And you realize, oh my gosh, this thing is loading 257 different things, all to render one page. Almost all of the things that it loads are actually static. They don't really change. That's why you get a 100 to 1 kind of read versus write ratio. The favicon for your favorite websites are not going to change very often. The banner is not going to change very frequently. If I have to load 257 things over the internet, I want it to be fast. How do we make things fast when, in fact, the individual operations are slow? How do we make things look like they're fast? This is a very basic question. Because I know that Margo would have talked about this in 313. Yes, right. And what is the downside to caching? Cache invalidation. Caches are great, and cache invalidation is a bitch. Seriously, it is hard. But we have to use caching in order to make anything work in these systems. And this is why that consistency versus availability thing is going to become really important to us. Because if we insist on a really strongly consistent cache, we're going to find out that it's a lot slower. In AFS, one of the things that was really cool about it is that we literally could take a computer, a Unix workstation, and at the University of Michigan, they did this for a long time. They could put 22 files on the local disk drive, and they could get everything else by fetching it over the network, and it would store these things in the cache. And what was amazing is it would all work. And this was when networks were way slower than they are now. So the reason the internet works, the reason that networking in general works is because we do a lot of caching. Facebook is very much as it's an old-fashioned company, they do use modern techniques, including caching. In the internet, we cache objects, and we cache them in a key value store. What is the key? Gosh, it's the path to get to the object. What's the value? It's the data of the object. Facebook did not invent memcached, but Facebook did actually extend it and give it additional capabilities of working in a distributed fashion that resulted in a paper they presented at NSDI in 2012. So within your lifetime, better than some of the stuff I've been talking about. And then a few months later, they presented a different paper, this one at OSDI, and that was about something called Tau, which replaced memcached at Facebook. Does that give you a sense of how long it takes to get papers published? They have different consistency models. Why is consistency important? I used variation of this earlier, so I might as well steal the same sort of presentation. You know, we have information that we want to be visible and information that we don't want to be visible. So it was like, you don't want your LinkedIn indicating that you have found a new job before you've resigned from your old job. You don't want the boss to know that your friend Sally is actually well when you're telling everybody that she's sick. So there may be ordering constraints. What do you actually want them to be able to see? Well, this is a whole bunch of distributed state. We can do replication to make it more available and tolerant to individual failures. So part of the internet goes away, we can still get our data. There are very big companies, Akamai, for example, been around for a long time. This is really all they do. CloudFront, pretty much all they actually do is cache state. And you can build really big companies. And these are companies you generally hear a whole lot about, but everyone ends up using them. Caching improves performance, there's no question of that, and it allows us to handle a broad class of failures. And then we figure out we didn't cover one. Mostly what we've been talking about, because we've spent a lot of time talking about Paxos and we've talked about Project 4, is strong consistency. Paxos, RAF, PMMC, view stamped replication, they all give us linear consistency. What is the point of replicating a log? The point of replicating a log is that we end up with an exact identical copy of the order of operations that need to be applied to this database to make it consistent. What's the problem with that? Well, since you have now been hired to work for, there's a startup company that apparently just got a round of funding to build a lunar data center. I thought was great. It's like, cool. It might inspire a question for the final, actually. You've been hired, you finished your job, you've now been hired to work for this startup company to begin building this. And here's the service that you're responsible for designing. Got the slide cut off. Sequential consistency means that there's a guaranteed single order of operations. It doesn't actually require strict linearizability because it does allow us to have variations of things that are not causally related. Causal consistency is even weaker than that, which is we only actually order the things that are causally related. We enforce the happens before, but two things that are not causally related, we don't really care. Switch them around, it makes no difference to the outcome. That's where we get into the isomorphic paths. My plan is to actually put a lecture in here about replicated data types, which rely on causal consistency, because it's a very common model. And we build libraries and packages that will allow you to build applications that use simple causal consistency models. To understand them underneath, you have to go and look in this mathematical area of lattice theory, which is essentially the idea that there can be multiple paths. So you have an entry and an exit, and there's lots of different paths that you could go through, but the outcome is exactly the same, and that's what defines something that's causally consistent. And we talked about that early on when we talked about consistent cuts. And that one's very hard to sort of internalize because it's like, well, what do you mean? It's really easy to say, here, I have a linear sequence of events, just apply them to your database, you get consistency. Now you're like, well, I wandered this way and you wandered that way, but we both met at the restaurant. We got the same outcome. We maybe did different amounts of work, but we got the same outcome. But not insisting on lockstep turns out to actually be more efficient in terms of performance. And that's why these weaker consistency models become important. Eventual consistency, you can recover from transient events. network partition, a single server fails, we have a recovery mechanism where we can come back, we can restore the consistency of the database. Our simple key value store, very, very simple. You don't even need append. I'm always kind of interested in that they put append as an operation in here because, frankly, from a database perspective, you just overwrite. You don't really append, but okay, fine. The simplest of all key value stores is a put and a get. You don't even need to delete. Oh, sorry, once you've created it, you can't delete it. But we put a delete in there because, well, we don't need that key anymore. We can put an append in there because, we want to make it more difficult for you. You won't see a lot of real key value stores that use an append operation. But it's just a special kind of mutation, and it's useful when we're building these labs because it makes it easier for us to show you that you didn't quite get your ordering right because this says foo and that says bar and this one says bar and that one says foo, so guess what? And there actually are times I've used those kinds of techniques in debugging to see the actual order in which events occurred so that I can reason about them and debug them. memcached. There's actually a link to memcached.org, is the open source version of this. The problem we're trying to solve with memcached, and the reason that memcached exists, is because we want to optimize web page loading. Nobody wants to sit there and wait over their dial-up connection, downloading lots and lots of objects slowly. So we cache locally. Well, cache in your browser. Your browser actually caches things on your local disk. And then the other side of the connection caches things because we want to put them close to you. CloudFront's business is moving data from where it's stored to where it's consumed, so that if you are here in Vancouver, you'll be getting a copy of that data that is close to you in terms of the network time it takes to get it, so that you're not sitting there waiting for lots of slow events. And we can do some other things. We can put parallelism there, of course. So we can load all of those objects at once. Sometimes you'll see that. If you get objects where the size is not known in advance, the browser can't render it correctly. So sometimes you'll see objects that, once they do get rendered, overlap with other things on the screen. It is a simple key value store. It is open source. You can go look at the source code for it. Oh, it only actually stores things in memory. Literally, people will stand up a memcached and put 12 terabytes of memory in it. It takes about 10 to 12 hours. I did that analysis a couple of years ago. It takes about 10 to 12 hours if you have 12 terabytes of memory on a memcached server just to reload the cache. So of course, the next thing you'll do is you'll go, well, why don't I just store it on some disk then? Because it'll be faster. Yeah, it'll only take about 6 hours then. The numbers actually are quite scary when you get into the terabyte range. How long it takes to read things. 6 hours is a bit of an exaggeration. It's more about 10 minutes. Another example of a key value store is Redis. Redis is very commonly used, and in fact, TAU-D, which is the open source implementation of Tau that someone built from the Facebook paper. Facebook didn't publish the source code for Tau. Uses Redis underneath as its key value store. So what are they trying to do at Facebook? Well, Facebook is this big company. They have data centers all over the place. They want some fault tolerance. They want some load balancing. So they have individual clusters. We have clients, that would be our web servers, that are sitting on top of memcached, and then they are in turn talking to the actual databases where the objects are stored, file systems, databases, other key value stores. But then we also want to be able to do that across data centers. So cluster here generally means data center. We also need to be able to do that across data centers. So we can have geographically dispersed data centers, again, with copies of this data. This is where it starts to become a really big win to be caching these things. Because now I'm saving tens or hundreds of milliseconds of transmission time to get that object. And using the magic of networking, I can actually choose to send you to the network location that is close to you, where close is measured in latency. I'm going to choose the low latency connection for you. Just basic replication. When we talked about crack, we talked about chain replication. And in what we did in project 3, those are all different kinds of replication, but it's all the same basic idea. Replication makes a lot of sense in a case where you have reads that outnumber writes by 100 to 1. Lots of data that doesn't change very often, but you still have to get that cache invalidation correct. And that's where things get fuzzier. Memcached uses what's called a look-aside cache. It has a very large data capacity. It deals with hot data that has a high temporal locality. So the things that get fetched over and over again for the hot pages get fetched over and over again. And it's the same things. And they have, so you go to a page, you load all the same objects at the same time. That's the temporal locality aspect of it. Everybody starts accessing that same page, and you have hotspots. You have elements in your key value store that are being fetched extremely frequently. If you don't load balance properly, what will happen is it will all get slow because everyone will be hitting exactly the same server. This is why we end up replicating our key value stores. This is why we end up sharding them. This is the motivation for Project 5. This is a real world problem. This is really done to address this real issue. I know that Amazon actually says that the amount of time that people have to wait for a web page to load is proportional to the likelihood that they will abandon it. And that means you're less likely to buy stuff. And remember, we spend the most amount of money hiring CS people to get people to click on buttons to buy things. You laugh, but it's true. It's a cynical way of looking at it, but so we've got web servers that are doing gets and occasionally sets, talking to a cache. The cache can actually have what are called misses. Oh, I don't have that object in my cache. If I don't have it in my cache, then I actually have to go talk to the database. Sometimes the web server will talk directly to the database as well. That's the right thing to do when what we are doing is mutating state where our load isn't read heavy, it's actually write heavy. Because there's no benefit in caching the reads when it's mostly writes. This is crack versus chain replication. Initially, they actually implemented all of this on top of SQL databases. So memcached is a key value store that's caching objects that are fetched out of SQL databases. It doesn't have to be. It could be off of anything. It could be off of a file system. It could be off of other key value stores. From that perspective, we care. The cache itself is actually filled on demand. So in other words, maybe you vaguely remember virtual memory. Same exact trick. Oh yeah, we're gonna actually map that thing here, and we'll go get it when you actually need it. And that's basically what happens. Is you go to the memcache, and it doesn't have the key, and it says, okay, well I'll go load it from the original location, and I'll allocate some storage in the cache, and I'll store a copy of it here. And it does that on demand, and the reason we do it on demand is because it is surprisingly common for people to not access things that are stored in our databases. I was talking about hot pages earlier. Well, the flip side of that is there's an awful lot of very cold pages. Very cold pages. We can't afford to keep everything in the cache. So we use this kind of natural selection process. We only load things in the cache that we need. How do we keep our caches consistent? Well, what we do is we actually create what we call read-only copies of things. And we use some tricks like we put timelines, time limits on how long we're allowed to cache something. So there are strong cache consistency protocols where you literally can make strange noises. I just assume it's rats. It's probably Remy, actually. You can actually have strong cache consistency protocols, but I can tell you from personal experience that they don't scale especially well when you go to internet level. AFS was well known because it actually implemented a single global namespace and allowed you to access things all over the world. I could sit in my office. I was in Pittsburgh at the time. I could sit in my office and look at things that were stored at IBM Zurich. And it was just transparent. It was all part of the same namespace. And once I had accessed it, I'd have a cached copy of it. But the first time, it's slow. We had a strong cache consistency protocol. And there were limits to the scalability. Surprisingly, it worked pretty well, but there were definitely limits to the scalability. NFS used a different cache consistency protocol. It just uses a timer. So file data will be stored, cached for 30 seconds, and directory data is cached for 3 was the default. Those numbers are very arbitrary. They don't mean anything. In AFS, we actually had a different model, which was a notification model. So when something changed, the server would call back to the client and say, I'm sorry, but your cache is trash. So what we did was we created read-only data that might actually be old. We allow a window in which we can permit stale data, and we let the client tell us what they're willing to tolerate. So I've been talking about the abstractions and whatnot, and we started off with the abstraction that we don't want the client to even know we exist. We want this to be completely transparent to them. But then we say, well, you know, if we bend the rule there and we make it visible and you can have the client say, do you want to pay the expensive price of getting the latest copy, or are you willing to live with yesterday's news? And the client says, you know, I'm just going to use it to line the birdcage, so I don't care if it's yesterday's news. Fine. And now you get a faster answer. But if you insist on having the authoritative answer, then you have to go back to the actual data location. So our caches are non-authoritative. And if you want an authoritative answer, you have to set a flag that says, I need the authoritative answer here. I'm making a hard decision. I have to be using the correct data, not I'm lining the birdcage with the newspaper. The lessons from MCached were that it actually is, stale data is a real problem. They came up with this nice solution where they made it visible to the client so the client could decide what they're willing to do. And we see that a lot. When we start building real world interfaces, we often do expose the realities to the client. You know, fast or expensive, take a pick. And these are engineering trade-offs. They're not the kind of thing that Lamport's going to be concerned about. He's a mathematician. He wants to be able to prove things. You want to be able to make broad, sweeping statements. When you're an engineer building this stuff, you have to actually make it work for the real world. This is why that lunar data center is very exciting. Kind of a combination of both. So one of the solutions that they used is a mechanism that's known as a lease, which I always think is great because I actually was working with Chariton when his grad student did the paper on leases. And leases are essentially this idea that when you get something for your cache, it has a time to live. It's not a really complicated idea. And the term lease gives you exactly the right idea. You know, this is my stuff for this period of time, and I know that I can cache it for that long. So now you have a bounded amount of time when your cache could potentially go stale. in the case I was talking about with AFS, we had a stronger guarantee, which was we had a callback, which said, we gave you a piece of data, and if that data changes, we will send you a message. So the period of time where that data might have gone stale is smaller. Whatever the latency is for me to get you a message. Now, if you're partitioned off the network, you could be using stale data, liveness versus correctness. Hey, we're back to the same exact problem again. Facebook, do you care? Probably not. Does anybody even use Facebook anymore? Right, pretty much, exactly, right. And WhatsApp, which is always disgusting. Touch Facebook, it makes me feel dirty. Remember people's birthdays. Yeah. Oh, so it's an extended personal assistant. Yeah. Great. Yes. I've heard that. I've actually never used Marketplace. I gave up on Facebook a number of years ago when I received 4,000 friends requests and realized that the only way to get rid of them is to go through them one at a time. There is no bulk, screw you, all of you people. And I was like, and so I stopped using it. And you know what? I didn't miss it. So once a year I'll go on and say, oh, yeah, look, another 400 friends requests have come in the last year. Leases are an interesting technique here where we have a time bound. It allows us to deal with lots of problems. So we go and we get something on a cache miss. What we get back is a time bound on that. Here's how long you can actually keep it in your cache. And that's built into the HTTP protocol these days. It actually tells you how long it's safe for you to cache something. We can detect concurrent writes and maintain write ordering because, of course, we're going to write it back to the same location. Yep. It's the idea that everybody chases after exactly the same object all at once. The first time I heard that was in operating systems, you can block and wait for something to happen. And what will actually occur is when you get enough threads all waiting for the same thing to happen, like a work queue, traditional thing. So you have 20 worker threads sitting on waiting for something to get injected into the work queue. And you wake all the 20 threads up. They all wake up, everyone gets scheduled, but there's only one work item. So only one of them actually gets to do anything. So they literally, it's like you open the gates, all of the horses come out, they all gallop around, and they all come back to the paddock, except the one who actually did something. It's not something that we really understood when we were building operating systems in the 70s, and it became very apparent as we got a lot more multi-threading and multi-processing and whatnot. And when you've got a 4 megahertz processor with a single thread, don't see a whole lot of thundering herd because you probably only got 6 threads. Now you sit down in front of a modern computer system and you realize, gee, the operating system process has 455 threads. Yes, it becomes a real problem. So the lease model, along with the flexibility of the client to specify whether they were willing to live with stale data or not, gives us much better performance in the common case where the clients don't actually care that they're using yesterday's favicon instead of today's favicon. Lots and lots of interesting stuff that comes out of this because it's very practical work, right? So, scaling. One of the interesting things they used was consistent hashing. This is a great idea. You're going to find that consistent hashing is how you can actually realize the ability to add and remove servers from a collective. I was thinking of the Borg when that, but that's probably too old. Does anybody remember Star Trek? The Borg? A couple of people. All right, fine. They're still making Star Trek shows and movies, so it's not like it's totally forgotten, I hope. At any rate. The consistent hashing model is one that's independent of the number of servers, which is why it's good for reconfiguration, so that we have a way of sharding up our key value stores in a way that distributes the data out. And if we need to, we can add an extra server. And if we have to, we can take a server away and not break our replication model and not require that we rebalance everything. That's the really interesting problem when you get into reconfiguration, which is something that PMMC talks about, for instance, and Raft talks about, and even Lemport talks about the potential for reconfiguration. He treats it separately, that a configuration change is nothing more than just one more proposal that you put out to the to acceptors. The configuration is, here's the set of servers. Well, consistent hashing is useful because it means you don't, the way you hash things isn't reliant on how many servers you have. Because the naive thing is to say, okay, I got 6 servers, so I'm going to give you 1/6, then I'm going to give you 1/6, then I'm going to give you 1/6. Then you sit back and you go, well, that's probably a bad idea, isn't it? Because that now means I have 6 points of failure, but it'll only take 1/6 of the database out. Congestion was a big problem for them. The scaling point. All web servers talk to all memcached servers. Remember when we were talking about how you can have learners and acceptors and proposers, and you can have multiple proposers. Well, what is kind of cool is that what they end up with is a model where effectively they end up with multiple proposers in their environment, and it's that geo-replication thing that starts to become useful for having multiple proposers. You might have a distinguished proposer in each of your data centers. You don't want everybody proposing, but having a single proposer in each of your data centers means that logically what's going to end up happening is the requests that come into this data center are going to go to that single proposer, who's then going to send them to the other data centers, and eventually we'll be able to reach consensus that way. So we started off by saying, yes, this is possible, but let's just ignore that for a minute. And then you get into the real world and you realize there are actually uses for it. There's a reason we didn't just exclude it from the underlying protocol. Congestion is a huge problem. Networks are like driving in Vancouver, right? You're driving at 6 a.m., nobody's using the roads, or very few people are using the roads, and so it's very easy to get from point A to point B. And yet the same trip at 5 p.m. turns into a nightmare. How many of you commute? One person, the rest of you, 2 people, the rest of you just roll out of bed and wander over. That's probably the best way to do it, because commuting in Vancouver can be kind of a pain in the neck, right? Gee, I live in Abbotsford. I tell people Abbotsford is 3 hours away from downtown Vancouver. I've driven it many times and it never takes less than 3 hours. And I guess that's just because I don't drive it at 6 in the morning. And 6 in the morning, it's what, like 45 minutes or something. There's nobody on the roads. Same thing with networks. Exact same thing. Roads are networks. It's just easier to visualize the roads because we've experienced them. Whereas, packets flowing through the internet, usually you just hit a website and you go, oh, it's slow. Why? I don't know. I'll just abandon it and go look at some other site. So they helped limit some of the network bottlenecks by limiting how many outstanding requests they would allow any individual server. So you've got a knob. Fast, slow. Fast, slow. The flip side is that if you make it fast, it's because you only allowed one car on the road. So if this is your day in your lifetime to drive, you can go anywhere you want really fast, and no one else will go at all. That's the problem with that knob. It's a choice between how many clients am I willing to give service to versus how long does each client have to wait. Multi-cluster redundancy was really interesting because, of course, now we have separate failure domains, and it required that they really think about how you ensure consistency. And gosh, it means that we actually needed to have consistent logs. This is like what we started talking about today, right? We need to make sure our logs are consistent. And so what they ended up doing was actually just using the the database level logs. I did like mixed squeal. Apparently, broadcast, I'm squealing. I guess. I looked at the picture, I said, that's kind of weird, but it did stand out. McSqueal face? Squealy McSqueal face? I don't know, whatever the meme is there. Okay, so now we're going to replicate it, because of course we've got to get it geo-distributed. We just add storage layer replication. And now we replicate our disks. And I will point out that the very first use of Paxos was in fact a replicated disk solution. Pestle. So a web server that wants to make a change actually writes directly to the database. Let's see, set a remote marker. So we tell the memcache that we're going to change this value. Then we actually do change the value. Then the database gets replicated to the server, and then we tell memcached that we've updated that value. So this actually provides us with a closed loop for updates. Who knew? I've been talking about consistency models, so I'm going to dive into this a little bit more. Causal consistency isn't enough. Word. The problem is that when I if I accidentally reset the slide, well, I didn't accidentally. When I reset the slide, what it actually does is, it's going to annoy me until I fix that one. Go with the other one. Oh, you're gonna make this difficult. I hate PowerPoint. Ah, there it is, okay. Much better. Slide, there we go. Doesn't quite do it right. I mean, small cutoffs I could ignore, but that one annoys me because all the text is gone. So one of the complications with causal consistency is that we can have invisible causal dependencies that stem from application semantics, right? So the application has this implicit assumption that it understands causality, and we have no idea. This is the sort of multi-reader-writer situation I started talking about at the beginning of the day. Not imaginary, it actually really happens. So we have, and this gets pretty bad as we begin to create georeplication, because we don't necessarily have instantaneous propagation of our updates between our data centers. So this increases the window in which I might do a read and then write something, but the read that I did has been updated, or it's not the same in the location where I'm writing it to. This is a real problem that you really see with S3. S3 doesn't actually provide a guarantee that if you write something and then read it back, that you won't get an old copy of it, because you may not be reading the same copy. It's replicated, and it's eventually consistent, but eventual consistency becomes quite complicated to reason about. I mean, in essence, when I was looking at this years ago, I said the only way to use S3, where you want to know that what you're reading is what you wrote, is to never write it again. Because then the only answer you can get is, I don't know what that is. So you do a get and you get back no key found, in which case that's a propagation delay and you can detect that. Or you get the answer back. If you want more than that, you end up having to put some sort of a versioning on top of it. Lamport clocks, which is a solution in a case like that. So there's some very recent work. This is from 2021, which is definitely within your lifetime. Was this paper called Cluster of Order Preserving Servers, where they have causal consistency in a wide area network. It's actually very interesting, and it does it with a lock-free, wait-free model. It's not actually using locks to provide this consistency guarantee. The link there is to the actual paper if you're interested. So part of this relies on being able to add logic in the client itself. Now we hide that complexity by putting it in a library, so the client doesn't really have to change, but we're implementing part of the consistency in the client itself. So this is a sneaky way of making the client aware of the fact they're running on top of a distributed system. So remember, we started off with this model of the client shouldn't know at all to, well, okay, the client shouldn't know, but in this case, we're going to hide that knowledge inside of a library we provided the client. So the client is now aware. It's just we've isolated that awareness. This is a pragmatic approach to solving a complicated problem. And it's cool as a result of that. I mean, it actually is very interesting, where they end up with this causal replication across geographically dissimilar data centers. In a get operation here, you can actually talk to a local copy, and it's that library is actually going to be what serializes this to make sure that you're getting a causally consistent version of it. And here's the picture from the paper where they do a change. And so what they have to actually do is replicate that change out and now force the ordering of that change relative to any of the gets that might be dependent upon it. Now, what's fun about this is you're really only dependent for things here if it's visible within your data center. Because if your client is talking to a different data center and it hasn't seen the put or the get, then we can just give you whatever the copy of the data is locally. Because remember, the idea is that we're trying to provide you with a consistent view. It doesn't have to be the most current consistent view. It just needs to be a consistent view. It's kind of like I'm running Paxos in the local data center, and then I'm running a different level of Paxos in the distributed data centers. You seem skeptical. I don't blame you. I mean, I'm mostly throwing this out here because it is an interesting paper. And if you really want to dive into something because you have an excess of time on your hands, here's a good paper. Actually, it is right. It's consistent within the data center, right? It's not necessarily consistent. If that client is talking to different data centers, then this isn't going to help you. But it is going to keep you consistent within this data center, even though we have multiple replicas within this data center. So it's like we're willing to pay so much for our consistency, but not so much that we encompass the entire universe. This is going to be important for your lunar data center design, isn't it? And so when you actually do these special puts, they define what you're dependent on. In other words, what have I already shown the client in this case? And that way we now know we have to order this put after these other puts or these other gets, or these other operations. So we talked about consistency. I've talked about consistency before. This was just much more of a hands-on-y kind of motivation for this. Look, this isn't something I just randomly made up. This is actually something that really happens in the real world. And you're going to see more of this because we've spent a lot of time wrapping our heads around very abstract concepts. And now I want to nail them down and say, this is why this stuff, A, matters, and B, is actually really, really hard because we talk about Paxos and how we elect a leader. And then once we have a leader, we talk about how we elect an owner for an individual location in a linearized log. That's Raft or PMMC. And then we kind of hand wave it and leave as an exercise for the reader to figure out how you get the data into that log. I don't care. Use heartbeats, put it on Facebook Marketplace. I don't really care. It makes no difference. Because that's now an engineering problem. Doesn't make it easy. Because when you're actually building this system, you probably will spend as much time on trying to make sure that you know how you're going to get that data into the log. But understanding That's the problem. And the way it's structured will make it easier for you to build that solution for the design of your lunar data center. And we'll leave the Martian data center to someone more capable. Any questions? There are 9 people in the class today. That's less than Tuesday. I didn't actually check to see how many people, if anybody, dropped the class or not. Kind of a hard class to drop if you require it for graduation and you drop it, then you're not going to graduate. You're going to stick around for another 6 months or a year. That sort of sucks, doesn't it? I know, I saw some people panicking about, passing a course. Don't panic. Yeah, exactly. Yeah. I mean, I can tell you, because I've now done this class 5 times at Georgia Tech, or a variation of this class. And Georgia Tech uses an A, B, C, D, F scale. And I think a D was like 35%. Because they don't post percentages, they only post letter grades. And that's basically how you hide the scaling. A C was usually like 45%. And I think a D here is 55%. Yeah, you have to work really hard. I mean, my machine learning class at Georgia Tech, the median percentage was like 55%. And that was enough to get a B. I mean, once you decide you're going to scale things, all bets are off. Usually the people you want to not actually pass the class, and you don't really want anybody to not pass the class, but for an online program in particular, what I've noticed is that there's always people who sign up for the class and then they never do anything. Those are the people who will end up failing the class. That's how you get an F in a class like that. People who actually try and do the projects and figure things out will normally get at least a C. Really hard to get a D in that class. But it happens. And yeah, it's not uncommon. I mean, don't expect that if you're going to get, it would not surprise me if half the class had less than 60% on Project 5. Seriously, it is hard. And I've made it simpler than the grad version of it, because I took 30 tests out that tested even more hairy, nasty, ugly side issues, ordering issues. So, but you're stuck now, except of course you're not really stuck, because you can always apply for late withdrawal. Most people don't even know that exists. And yet it's kind of fun, because being simultaneously at multiple universities, you get to learn that they all do things pretty much the same way. So every rule has someone who can overrule it. There's always some mechanism for getting something because you have an exigent circumstance. I mean, the first class I took here, I applied for a PhD, and the person I wanted to work with met with me like 2 days after I submitted the application. And he said, well, you should take my class, which was in January. Now, this is literally like the 8th of December or the 10th of December. And so in order to take a class here, you have to be enrolled. There's unclassified. You have to be at least an unclassified student. I qualified to be an unclassified student, but the deadline for that was like October. I actually registered for that class as an unclassified student over the winter holiday break. And let me just say, that was like moving mountains to get that to happen, but I did it, and you can do that. There's always someone who can sign off on these things. And I asked that person to give a talk. He originally said yes, and now I've asked him twice for an actual concrete date and time, and he hasn't responded. So we do have a talk on Tuesday. This will be Royal O'Brien, who is executive director of the Open Metaverse project for the Linux Foundation. I don't know if you've ever heard of Linux, but it's this esoteric operating system that a couple of people actually use. You might not have heard of Metaverse, but that is, of course, about the idea that living in virtual reality can be way more fun than living in actual reality. And his goal is to help people actually come up with interoperable standards so that if you buy your really flashy Nike sneakers in one metaverse, you can actually see them in another. Very important stuff. His background is a lot of gaming, scaling up games and whatnot. So that's where he's coming from. So it should be an interesting talk. He's a very interesting speaker. And he was, before he joined the Linux Foundation, he was actually at Amazon for 4 years promoting their game platform. And basically the last thing he did was convince their soon-to-be CEO, Jassy, now the CEO of Amazon, to spin off all of that work and give it to the Linux Foundation, which is why he's not the Linux Foundation. But he's in Jacksonville, Florida, so that's why it's going to be on Zoom. And that's it. Thank you, everyone, and I will see you on Zoom on Tuesday. And I'll post on Piazza about that as well. Let me go find OBS, stop streaming.